Good morning, students. Today we shall begin a new lesson from the syllabus of class 11 physics. The name of the chapter is gravitation. Today's lesson will be dedicated to the discussion of three topics. We shall begin with Kepler's laws of planetary motion. Then we will discuss the universal law of gravitation given by Sir Isaac Newton and its importance, and we will understand what is acceleration due to gravity. So let's quickly start with the first topic, that is Kepler's laws of planetary motion. In 498 AD, the Indian mathematician and the astronomer Aryabhatta proposed that Earth revolves around the Sun and at the same time it rotates about its own axis. In 1543, the Polish astronomer Nicholas Copernicus advanced the idea that not only the Earth but all the planets move around the Sun in circular orbits, the Sun remaining at rest. Kepler reduced the large number of observations of the planetary motion made by Tycho Brahe to three laws known as Kepler's laws of planetary motion. Now these laws can be understood one by one with the help of the diagram that you can see right now coming on your screen. These actually represent the three laws of planetary motion given by Johannes Kepler. Let us start discussing with the first law. The first law is called law of orbits, according to which each planet revolves around the Sun in an elliptical orbit with the Sun at one focus of the elliptical path. Each planet revolves around the Sun in an elliptical orbit with the Sun at one focus of the elliptical path. Now let's go back to the previous picture and refer to diagram A. In this you can see that the planet is moving around the Sun in an elliptical path and Sun is present at one of the fixed points named as the focus. In fact, an ellipse has got two fixed points that we name as focus. The Sun is present at one of the two focus. Going to the second law. The second law is called law of area. The statement of this law goes something like this. The position vector of the planet from the Sun, this means the line joining the planet to the Sun sweeps out equal areas in equal time. This means the aerial velocity of a planet around the sun always remains constant. The position vector of the planet from the sun, that is the line joining the planet to the sun, sweeps out equal areas in equal time. This means the aerial velocity of a planet around the sun always remains constant. Now let's again go back to the figure B. Now as you can see in the picture that two shaded regions have been shown. If this is the position of sun, so if the planet takes the same time while going from position A to B as it does in going from C to D, then according to second law, the areas ABS and CDS are equal, as these areas have been covered in the same time. Since the areas ABS and CDS are equal, the length of the path CD is greater than AB. It follows that whenever a planet goes away from the sun, its velocity decreases, and as it approaches the sun, its velocity increases. This is the second law of planetary motion. Coming to the third law, which is called law of periods. The square of the period of any planet about the sun is proportional to the cube of the semi-major axis of the elliptical orbit. So if T is the period of the planet, that is the time period of revolution, and R length of the semi-major axis of elliptical orbit, then T square is proportional to R cube. So if T1 and T2 are the periods of any two planets and R1 and R2 the respective semi-major axes of their orbits, then we can write down T1 square by T2 square to be equal to R1 cube by R2 cube. Now actually R will refer to the average distance of the planet in place of semi-major axis. Further, if the orbit of the planet is taken as circular, R will stand for radius of the circular orbit. These three laws together constitute Kepler's laws of planetary motion. Now let's get over to the universal law of gravitation. Newton's law of gravitation states that every body in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of distance between them. Now this means it is inversely proportional to the square of the distance between their centers. So as you can see in the diagram also it has been shown that there are two masses m1 and f2, and these two objects are attracting each other if suppose the distance of separation between their centers is r. So if F is the force of attraction between these two masses, then as per this law, F is directly proportional to m1 m2, that is the product of their masses, and F is inversely proportional to the square of the distance between their centers. So combining these two equations, we get F to be proportional to m1 m2 by r square. And as we all know that if we want to replace the proportionality sign with an equal to sign, we have to introduce a constant. So this constant is given by the alphabet G, capital letter G, and then we can write down the expression for force to be equal to F given by G m1 m2 by r square, where G is the constant of proportionality called the universal gravitational constant. Now if suppose m1 is equal to 1 kg, m2 is also equal to 1 kg, and the distance between the centers of these two masses is 1 meter. Then in that case, if we substitute the values in the equation for gravitational force, we get F to be equal to G 1 into 1 by 1 square, which further implies that F is equal to G. So using this expression, we can give a definition for the universal gravitational constant. This means universal constant of gravitation is numerically equal to the force of attraction between two unit masses placed at unit distance apart. So universal constant of gravitation is numerically equal to the force of attraction between two unit masses placed at unit distance apart. The value of this constant does not depend upon the nature and size of the bodies. It also does not depend upon the nature of the medium between the two bodies. Owing to the extremely small value of gravitational constant, the gravitational force between even two big rocks is very small. The value of G is actually 6.67 into 10 to the power minus 11 Newton meter square per kg square, and its dimensional formula is m to the power minus 1 L to the power 3 T to the power minus 2. The value of gravitational constant was first determined experimentally by Henry Cavendish by using a torsion balance. Acceleration due to gravity. The Earth attracts every other body lying near or its surface towards its center. The origin of this force between the Earth and a body is due to the interaction between their masses. The force of attraction exerted by Earth on a body is called the gravitational pull or gravity. We know that when force acts on a body, it produces acceleration. Therefore, a body under the effect of gravitational pull must accelerate. So, the acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity, and it is denoted by alphabet G, small letter G. The value of acceleration due to gravity does not depend upon whether the body falling under gravity is a light one or a heavy one. That is, the value of G is independent of the mass of the body. Near the surface of the Earth, the value of acceleration due to gravity is 9.8 meter per second square. Now, let us obtain an expression for acceleration due to gravity. For this, let us consider a figure somewhat like this, in which an object of mass m has been kept on the surface of the Earth. Now we shall mark the radius of Earth as r and mass of Earth as capital M. So consider that the Earth is a sphere of mass m and radius r, and a body of mass small m is lying on the surface of the Earth, as you can see in the picture. If the size of the body is very small as compared to that of the Earth, then the distance between the center of the body and that of the Earth will be approximately equal to the radius of the Earth. Therefore, The force of attraction on the body due to the earth is given by F equal to G m by r square. Now, the force F on the body of mass m due to the earth produces acceleration due to gravity in the motion of the body. Therefore, force on the body due to earth is also given by F equal to m into a. Now, in this case, acceleration is acceleration due to gravity. So, F is equal to mg. Now, if we consider these two equations as 1 and 2, then from equations 1 and 2, on comparing, we get m into g to be equal to gmm by r square. We can cancel m from both the sides, and therefore we get the expression for g to be equal to gm by r square. Now this gives the value of acceleration due to gravity at the surface of the earth. Now, assuming the earth to be a uniform sphere, if we are asked to calculate the value of acceleration due to gravity, then we can do so in the following way. Mass of earth is 6 into 10 to the power 24 kg, the estimated value. Radius of earth is 6.4 into 10 to the power 6 meter. And as we all know, the value of universal gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per kg square. So now, substituting in the expression for acceleration due to gravity, since g is equal to gm by r square, so that will give us 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 divided by 6.4 into 10 to the power 6 whole square, and we can put the unit as meter per second square. So on calculation, we get g to be equal to 6.67 into 6 gives 40.02, and the power of 10 comes out to be 10 to the power 13. In the denominator, we get 6.4 whole square, that turns out to be 40.96, and the power of 10 becomes 10 to the power 12. So eventually the value comes out to be equal to 9.8 meter per second square on the surface of earth. Now at this point, I would like to mention the kinematic equations of motion under gravity. Now, when a body falls freely under gravity, it is accelerated towards the center of the earth with an acceleration of 9.8 meter per second square, called the acceleration due to gravity. Thus, kinematic equations of motion under gravity can be obtained by replacing A by G in the kinematic equations of motion obtained in our previous discussions. So, accordingly, the kinematic equations of motion under gravity can be written as, like if you remember, we have written V equal to U plus AT, which will now become V equal to U plus GT. Then we have done S equal to UT plus half AT square, and in this case we can replace S with height H, and that will be written as UT plus half GT square. Then we had studied V square equal to U square plus 2AS. So now we can write down V square equal to U square plus 2GH. And finally, we have studied Sn to be equal to U plus half A 2n minus 1. So in this case, we can write down Sn to be equal to U plus half G 2n minus 1. So these are actually the kinematic equations of motion under gravity. Now we shall end today's discussion at this point. In our next video lesson, we shall discuss about the effect of different parameters on the value of acceleration due to gravity. So the topic of discussion for the next video lesson would be variation of acceleration due to gravity. Thank you.